Thanks a lot for inviting me to speak and for the very nice introduction. Yeah, so I'll be telling you about some recent developments on the theory of Markov chain mixing times, which are sampling algorithms that we will see, which has been, this recent framework has been really useful in resolving some long-standing open problems and has really built new connections between the theory of Markov chains and other areas. So everything I say will be based off of various joint works with these folks. This is not a single paper, but okay. Okay, so let's get started. So, okay, so here's the fundamental problem that I'll be interested in. Okay, so I have some probability distribution mu. Please feel free to just be rude and interrupt me whenever, just if you have questions. Okay, so I have a probability distribution mu, and you should think of it as being very high dimensional or supported on an exponentially large domain. So for instance, just for concreteness or for convenience, let's say it's supported on the Boolean cube. Okay? And what I want to do is algorithmically draw samples from this distribution. Okay? So goal. Draw samples. Okay? And maybe some examples just for concreteness to keep in mind. So of course, so we're mainly interested in the discrete setting. So we have very classical, say, combinatorial models. So let's say uniform over, classically studied combinatorial objects, like let's say spanning trees and graphs, say colorings, matchings, and so on. And maybe an example of like a non-uniform distribution that you might be interested in is the following. So I'll typically write sigma to be like a plus minus 1 vector, or some element of the domain. And another class example is taking mu to be proportional to the exponential of a quadratic form. Okay, so this is a classic example in statistical physics called an Ising model. It's also used a lot in like machine learning. You should think of A here as being some kind of weighted adjacency matrix of a graph with positive, possibly negative or positive entries and so on. So these are just some like concrete examples of what you might be interested in sampling from, although certainly not an exhaustive list. Everything I tell you today will be sort of a general theory towards this. Okay. Okay. So basically, I want to do algorithmic sampling. Oh, sorry. Yeah. I mean, I can make A to minus. It's not a big deal. Yeah, I'm keeping these generic. Yeah, but yeah, good question. Okay, so really one of the, I guess maybe I should say, maybe it's okay to say dominant approaches, both in theory and in practice, is to run Markov chains. Okay. So, and if you don't know what a Markov chain is, let me just give you an example that I'm going to study throughout this talk. Okay, so this is something called Glauber dynamics. This is one of the simplest examples of a Markov chain. So it goes by the following process, random process. So let's say I start with an arbitrary sigma. Okay, so let's say plus minus 1 for now. And each step, so I'm just going to run the following two-step procedure, and I'm going to iterate. Okay, so first I'm going to pick a uniformly random coordinate I. Okay, and then condition on everybody else, I'm just going to resample only this single coordinate. Okay, so resample sigma I. Conditioned on everybody else. Okay? So maybe for concreteness, if I'm looking on the Boolean cube, what I'll do is I'll flip sigma I with probability with this probability. So here I just mean I take sigma, my configuration sigma, and then I just flip the ith coordinate. Okay? So with this probability, I'll flip the ith coordinate, and then with the remaining probability, I'll stay where I am. Okay? So this is Glauber dynamics. So a couple things. First, typically, I actually don't know, I cannot actually compute the value of this thing because the distribution is given to me in unnormalized form. So I typically don't know the normalizing constant. But even still, I can still run this dynamics. I can still implement this efficiently because I only care about the ratio of these two probabilities. Okay, so the normalizing constants cancel out, and this dynamics is actually implementable. Okay. The second thing is that, so under very mild assumptions, such as connectivity of like the distribution or the state space of the distribution under these transitions, and we have that if I start from any, so let's say for all starting state sigma, that if I look at, so if I start from that state sigma and I run t steps of the random walk, and I compare the resulting distribution with the distribution I actually want to sample from, then in total variation distance, this is going to 0 as t goes to infinity. Okay, so just to make sure we're all on the same page, so here, this is the transition probability matrix. Okay, and if you don't know what total variation distance is, you can just think of it as being, like I view these as like big 2 to the n dimensional vectors, and I take the L1 norm, or L1 distance. Okay? So under very mild assumptions, if I start from arbitrarily and I just run the dynamics for sufficiently long, I'll eventually get to like a true sample for my distribution. Okay? Up to a little bit of error. But if I want to, I guess the key question here, though, is that, I want a quantitative bound on this rate of convergence, right? If I want efficient algorithms, I want this convergence. I want to be able to get to epsilon in like time polynomial in n and like log 1 over epsilon. Okay, so we'll say the Markov chain is rapid mixing if let's say this. Say, okay, I'll just write this. So we'll say the Markov chain is rapidly mixing if basically this total variation distance, the most epsilon for t, the most polynomial in n, and like log epsilon. So even though I have an exponentially large domain, I can still, what I want is an algorithm that samples in polynomial time. Okay, polynomial in dimension and, say the parameters, the error parameter. Okay? So is the algorithm clear? So I'm just going to run this two-step process from some arbitrarily chosen starting state and hope that in polynomial number of steps of running this process, I eventually get to like a bona fide sample, like up to some small error. So really the key question is like, how can you establish rapid mixing? Okay? And I guess this is one of those questions where you kind of really want theory to, for this problem because like there aren't really, as far as I'm aware, like good ways to algorithmically test if your Markov chain is already mixed or not. Okay? So this is one of the things where I think theory is important. So I guess the main purpose of this talk is to tell you about like a recently emerging framework for studying this question. Okay? And also like tell you about like connections with other areas. So this is what is spectral independence. So I want to find this notion of spectral independence. So this turns out to be a property of just the distribution mu itself. So actually, it really has no reference like the dynamics that I chose here. Okay. Okay. So to define spectral independence, let me first define a notion of an influence matrix. So define influence I onto j as follows. So I'm going to look and call it psi sub mu. And it's going to be given by the following difference of conditional marginal probabilities. Okay, so it's the probability if I draw a sample from a distribution mu, that it assigns the ith coordinate to, say, +1, condition on it knowing that the ith coordinate is assigned to +1, minus the same probability except now I condition on the ith coordinate be -1. Okay. So for all I and j, I can look at this difference of conditional marginal probabilities. And this is really capturing some notion of correlation, or at least I personally like to call it an influence, because you're asking for how much does knowing the value assigned to coordinate I influence the probability that j is assigned +1. Okay. So we'll say that mu is eta spectrally independent if the largest eigenvalue is upper bounded by 1 plus this parameter eta. The 1 there is just kind of for technical reasons, just because on the diagonal when I is equal to j, the influence is 1. Okay? That's just for technical reasons. Okay. So I guess I should say that there's another way to think about this. And it's in terms of something perhaps maybe slightly more familiar to you, which is that an equivalent way to state spectral independence is the following. So definition. So I can impose an equivalent to state is to say if I look at the covariance matrix of the distribution mu. So I have a distribution where plus minus 1 vectors. I can look at the covariance. This is upper bounded in the PSD order by this constant times a certain diagonal matrix, where I guess the correct thing to put is the variance, individual variance of each coordinate on the diagonal. Okay. So this is perhaps another framing that's like using things that are more familiar to you. Okay. Okay. Questions about the definition? So maybe let's do like a couple examples. So yeah, very good question. So this matrix in general, it can have positive or negative entries. It's in general asymmetric, but because of this connection with the covariance matrix, it always has real eigenvalues. Okay, so this is actually, yeah, I should have said this is actually like well defined, but yeah, the question. So you can always think, yeah, so you can think of it as like this covariance bound, or you can think of it as bounding the eigenvalues of this influence matrix. Yeah, thanks. So maybe let's do like a couple examples. Okay. So Okay, so let's say I look at uniform distribution or plus minus 1 to the n, okay, or a product measure. So does anyone want to tell me what the spectral independence of this is? Exactly, right? So why is that? Right, so like all the off-diagonal entries are 0, right? I only have 1s on the diagonal, 0 everywhere else, so it is going to be 0. So this is 0. Spectrally independent. Let's do another example. So now let's say mu is convex combination of the following two distributions. So with 1/2 probability, it's all 1s. With 1/2 probability, it's all minus 1s. So does anyone want to tell me what the spectral independence of this is? Yeah, exactly. So why is that? Exactly, right? If I know in this distribution, if I know the value of a single coordinate, that tells me everything, all the coordinates, right? If one of them is 1, then all of them are 1, right? So the influences are all uniformly 1. And so in this case, influence matrix is it's just the all 1s matrix and has a very big eigenvalue. Okay? So you already, from these two examples, you can kind of see, so like what spectral independence is trying to capture, right? So on the one end, if we have like truly like a product measure, then things are very nice, and this is where we expect, you know, Glauber dynamics to be fast mixing and so on. And on the other hand, for this distribution, Glauber dynamics is not even connected. Okay? I have to flip n coordinates in one step in order to transition between these two states. Okay? And this is like kind of captured by this influence matrix. You can detect it with this influence matrix. Okay? So we want this, so I guess maybe I should have said earlier, like we want this eta parameter, the spectral independence parameter, to be small, like a constant, independent of n. Okay? Questions? Okay. So I guess maybe I'll say just first, so I guess the rest of the talk, and really the rest of this, both tutorials, is really just to, so I guess for this talk, I'll just state a few theorems, give you without proof, and give you like a couple examples. And really the bulk of these talks will be about how to establish this property. Okay, so in case if you have a distribution that you care about, that you want to sample from, maybe these tools can be of use to you. Okay, so that's really the plan for the rest of the talk. Okay. So. So what do I want to tell you now? I want to tell you, what you can get out of this definition. So suppose you knew your distribution is spectrally independent. What can you get out of it? Okay. So I'm going to state the following theorems without proof. So I guess the first theorem is really due to this work of 11 Lau, based off of some connection with this area of high-dimensional expanders, which I won't get into. And it says the following. So if mu and all conditionals so suppose my distribution mu is spectrally independent, and also that all of its conditional distributions are spectrally independent. So what I mean by that, I mean I can pick any subset of the coordinates, and I can assign those guys to plus or minus 1, and this induces some conditional distribution on the remaining coordinates. And I want that for all such conditional distributions, they're all spectrally independent. So it's kind of like a multi-scale kind of criterion. So if this is true, then let's say Glauber dynamics. Mixes in n to the 2 plus data steps. Okay. So in particular, if my spectral independence is upper bounded by a constant, independent of n, then I can get a polynomial mixing time, okay, which is efficient. Okay. Questions about this statement? Yeah.
So if you don't have the multi-scale, there are some methods for which the mix is fast, but then how do you compare what happens if you drop the conditional and just say, okay, say only use spectral independence?
Sorry, I can say.
So could you compare what happens if you drop the assumptions that the conditionals are spectrally independent?
Oh.
Could you paint us a picture of like, under like if beta is smaller than 1, it mixes fast, and like.
Yeah, if I understand your question correctly, so I cannot drop the condition that all conditionals. I mean, you can weaken this slightly, but you definitely cannot just look at only the unconditional measure. So that's only pairwise correlations. That's definitely not strong enough to give you spectral independence. I mean, there are examples where, that the unconditional thing is spectrally independent, but the Glauber dynamics is still not connected. So there are examples.
How about beta smaller than 1?
Oh, are you saying like to improve like on this running time, or?
I guess what I'm asking is like, can you compare it if we took the Bruch's condition?
Oh, yes.
Which requires beta smaller than 1 and doesn't require
Okay, good question. So I guess those things, they are morally trying to capture the same thing, but they're really quite different. So it turns out, okay, so this is a bit of a technical question, but if you have this thing called the Bruchian's condition, this will imply an upper bound on spectral independence, but not the other way around. Okay, so the Bruchian is really asking for like a stronger criterion that implies mixing. Okay?
But notice, like the Bruchian, I mean, it's still worst case boundary configurations, right? So if you take a second example, if I had something that was like 3Ys or KYs independent, you'd be host.
I agree, yeah. But I think it's an interesting comparison.
Yeah. I can tell you more offline about that, but yeah. Hmm? Yeah. Yeah, good question. Yeah.
Does this characterize fast mixing?
It does not. I mean, like sure, like there are definitely examples where like some conditionings are bad, but the thing is still fast mixing. Yeah, it's just like a sufficient condition.
Is it possible to define a similar sort of notion when you support it on like the sphere?
Sphere. Yes, I think so. Yeah, so you can also I think there's a way to formulate it also in terms of covariance matrices, but I won't get into it. Yeah.
In the second example, I should never understood it. Does this say that it mixes in end-to-end time?
Yeah, I guess I should. Good catch. So yeah, yeah. So I guess maybe I should say let's say it's also connected. So under a very mild assumption and spectral independence, that implies. Yeah. So it's also and. Yeah, good catch.
I can you explain intuitively why independence helps with mixing?
Yeah, good question. So I can give you, yeah, so here's a little bit of intuition. So first off, like, if I truly have independence, right, it's a product measure, then I know that it's fast mixing. So there are very simple coupling arguments. You can even compute eigenvalues explicitly and so on. I guess roughly speaking, you can think of, okay, so typically why would a Markov chain not mix, right? A Markov chain would not mix, roughly speaking, is if like you have some kind of like multimodality, in which case, Markov chain maybe gets stuck in here and takes exponential time to cross like this energy barrier, for instance, okay? Now, such situation, in some sense, can only arise if you have very strong correlations, right? Consider, for instance, here, like think of the modes here as being all ones and all minus ones, right? Somehow knowing the value of one coordinate completely determined all the other coordinates. So it's in the setting of like really strong correlations where you can form these kinds of bottlenecks in the state space. Okay, roughly like, intuitive. Okay, does that answer your question? Yeah, good questions. Keep them coming. Okay, So this is the first theorem that says, okay, if I have constant spectral independence, then I get some polynomial bound in the mixing time. But it's very sensitive to the value of this spectral independence. So if eta is 3, then this is the end of the 5 mixing, which a polynomial, but not practical, so to speak. So here's the second result, which if I make additional assumptions on my distribution, I can do much, much better. Okay. This is with Song Chen, who's in the audience. Maybe he should be the one giving this talk because he can probably explain this much better than I can. Okay, so I'm going to make the same assumption. So all of the conditionals are spectrally independent. So okay. I'm going to add 2 additional assumptions. The second assumption, which will apply to, for instance, to distributions typically on graphs, like say colorings or matchings and so on, is that mu satisfies what sometimes called the global Markov property. Or sometimes just more colloquially, just conditional independence with respect to a bounded degree graph. So let me just clarify what that means. So think of my distribution as being on plus minus 1 assignments to vertices of some graph. And I just want the property that if I condition on the values, the plus minus 1 assignments in all vertices in like some separator, that in the resulting conditional distribution, the configurations in these 2 halves are independent of each other. Okay, so in other words, think of it like, maybe as an example, let's say if I have a distribution over like matchings in a graph. If I have 2 graphs that are disconnected from each other, they have no edges between them, then the matching here is independent of the matching here. Okay. Does that make sense? And the third assumption is something a little more technical. It's just that all marginals of mu are order 1. Okay, this is just some extra technical assumption. You should think of this as holding, for instance, in these graph models when, say, the graph is bounded degree, for instance. Okay.
Sorry, what does the condition mean?
Yeah, so I should clarify what this means. So yeah, so I guess what this means is, like for all, say, conditionals, so maybe I can write out more fully. So essentially it's just that the probability that sigma of I is plus or minus 1, either one of them, they're both some constant, independent of n, and that this holds for all conditionings. Okay, so even if I condition on some other coordinates to be plus or minus 1s, all of the marginals are constant order. Okay, so say, yeah, does that answer your question? It's a bit of a technical assumption, but it's needed for at least some of these. Is necessary in some, for some. Okay, I won't go into details. Okay, so I just have 3 assumptions. The first is that I assume the same thing as before, spectral independence, but now I've added 2 additional assumptions. That it satisfies a kind of a conditional independence property and that all the marginals are bounded. Okay. And this implies that Glauber dynamics mixes in order of n log n steps with some constant depending on, I guess maybe I say, the maximum degree of this underlying graph and how good my spectral independence is. Okay? But at least in terms of dependence on n, this is essentially optimal. So if you know, for instance, about, say, Glauber dynamics on the uniform distribution of the cube, n log n is the right answer. And there are also lower bounds in many settings. So this is sort of the best thing you can hope for, at least in terms of dependence on n. questions? Yeah.
So, again, trying to understand, so what's the motivation for, say, having very fast mixing time? So is the hope that these global dynamics give me the fastest algorithm for sampling from the distribution?
Right. So typically, yeah. So these algorithms are run in practice, right? And we want them to actually run like efficiently, like rather than n to the 5 time. Yeah. So imagine you simulating some huge interacting particle system, n is huge, right? So okay. You really want something like as fast as possible.
Do we require any like quantitative notion of connectivity, or just it's connected?
Yeah, so I guess connectivity is just to avoid some like technical issues, but this thing is really the quantitative notion of connectivity. You should think of it that way. Yeah. Or there's one way to think of it that way, but yeah.
What does it mean for eta that you did in the substrate?
Sorry, yeah. So this just means that, okay, so maybe I should say, yeah, good question. So I just mean there's some constant depending on, which I'm not going to write, that depends on the eta and then the maximum degree. Yeah. More questions? So, yeah.
Again, sort of related to this. So are there natural examples where global dynamics is sort of not the fastest algorithm for sampling? Or maybe there's exponential gap between the best algorithm and global dynamics?
So let me think. I mean, there are definitely many examples where like it's not known like if Glauber dynamics mixes, but we have some other like at least like weaker sampling algorithms that are pretty fast. But
examples where you have exponentially slow Glauber, but the fast sampling.
yeah, sorry, yeah, and there's also like
There are tons of examples.
yeah,
Ferromagnetic easing model
Yeah.
in low temperature.
yeah, like there are other, for instance, there are like other more global Markov chains that will mix very fast, but this is
With exponential gap for
sorry, yeah, that's a better answer.
Could you explain one more time your marginal condition?
Yeah.
What is the theta in terms of?
So this is just some constant independent of n, some constant. So think of, for instance, maybe depending on the maximum degree.
One would be a constant independent of n. So does it mean that it's like bounded away from 0 and 1?
Sorry, yeah, yeah. So so maybe I'll say, yeah. So it's like, yeah. So it's like, like 1 minus c, or at least c for some small constant. Yeah. Sorry. Yeah. Yeah. Good. Good question. Yeah. More questions.
Sorry, just going back to the definition, like why does the greatest eigenvalue actually capture spectral independence?
I mean, that's the definition of spectral independence, I guess.
Yeah.
Or you're saying like, why does eigenvalue?
Bounding it. Why is a large eigenvalue make it less spectrally independent?
I guess okay. I guess that's a matter of like definition. But I guess the way to think about this is, okay. I mean, one answer to this is that or like maybe one way to prove this, for instance, is there's a way to prove this by relating Glauber dynamics to like a decomposition of Glauber dynamics into smaller walks, smaller Markov chains. And then the spectral gap of those Markov chains, or the mixing for those smaller Markov chains, turn out to be exactly controlled by, like there's a way to rewrite it in terms of like a condition on these influence matrices. Okay, as a rough high level. I mean, at the very least, it's just quantifying how far you are from product distribution, right? At an intuitive level.
Can you explain again what is with regard to Kuikui graphing?
Yeah, so good question. So I just mean the following. I just mean that, so imagine my distribution is on plus minus 1 assignments to vertices of the graph. Okay? Now I want the following property. So if I condition on the values of some vertices in a separator, so now these two, now I split this graph in half, and these two halves no longer talk to each other because there are no edges between them, that in the resulting conditional distribution, the distribution of configurations on each half, they're independent of each other. So basically, configuration here is independent of the configuration here. They don't influence each other. Okay, so I want this for every, yeah. Sorry, does that answer your question? Or does that make?
Look at this delta, like what's the rho delta?
Yeah, the rho delta is just quantifying the sparsity of this graph. So it's a sparse graph. So this is. this is like some graph G. Is that okay? More questions? Okay, sounds good. Okay, so now I want to tell you about like, so I'm not going to prove these theorems. I guess sort of my goal in this talk was to more tell you about like how you would verify a condition like this, okay? And then so that maybe it can be useful for you. Okay, so. I guess I'll first draw like a little diagram of like sort of like a list of techniques that we know how to use, and then I'll tell you about like one or two of them, because I won't have time to tell you about all of them. Okay? So we have this notion called spectral independence. So we know it implies fast mixing. It also has implications for, say, concentration. So there's a particular paper that I like about this by Kaufman, King, and Solda. This sort of goes directly from spectral independence to concentration. And now, what are the techniques that we know? So we know that, for instance, coupling, or various incarnations of it, will imply spectral independence. So maybe some examples of like applications that this has been used for, say like solutions like CSPs, like B matchings, B edge covers, so on. There's another technique, which I'll also tell you about, called correlation decay. So this turns out to be a very useful structural property of the distribution, which also implies spectral independence. It's useful, for instance, for colorings. For independent sets, and so on. And then there's some more algebraic tools based off of, say, geometry of polynomials. And I guess I'm running out of space. And there's also a technique called the trickle-down theorem. This is due to Oppenheim. And this is based off of a connection with the recently emerging theory of high-dimensional expanders, which I won't get into. But this is useful, for instance, for like spanning trees. Matroids, if you know what they are, and so on. Okay. So my goal for the rest of this talk, I guess I only have 15 minutes left. My goal for the rest of the talk is to tell you about, give you like a nice, like cute example, and that illustrates the coupling method. And then I guess the next talk will be about sort of this structural property of the distribution called correlation decay that is very important in like these, especially in statistical physics type applications. Okay. Okay. So, any questions? Oh. Okay. Okay, so I want to tell you about like maybe a cute example of how to use coupling to prove spectral independence. And I guess maybe just to have a concrete example or of a distribution that we'll be considering is the following. So let mu be a uniform distribution over all matchings in a graph G. Let's assume that the maximum degree of G is some constant, independent of it. Okay, just for convenience, so I have a sparse graph and I want to sample a uniformly random matching. All matchings, not just perfect ones. Okay, so what I want to prove using this coupling method is the following. So here's the proposition that mu is order delta squared spectrally independent. And this in particular implies that Glauber mixes n-log. So I guess I should say that this model was first studied in a very seminal work of Jerram and Sinclair, and we know that at least a slightly different dynamics mixes rapidly, even if we don't have the bound degree assumption. But I'm going to assume bound degreeness for convenience, and yeah. Okay. So this is what we want to prove. Okay. Okay. So here's the lemma. Which will sort of, you'll see like how coupling is related to spectral independence. Okay. So I guess maybe let's see. So I guess let me first say one thing. So I want to bound the maximum eigenvalue. It suffices to upper bound any matrix norm of this matrix. Okay? So suffices to bound. So the affinity norm of the matrix, which is really just the maximum over all coordinates I, the summation of J. Influence around J. Okay. So first, it suffices to show that for every coordinate I, if I look at the total influence of that coordinate I on all other coordinates, then that total influence is upper bounded by a constant. Okay. So here's the lemma. So for every, let's say, so now this is a distribution over subsets of edges. So my coordinates are essentially edges in the graph. So for all edges E, if I look at the summation for all other edges F, the probability that F is in my matching, condition on E being in my matching, minus the probability that F is in the matching, condition on E being not in the matching. So this is the influence. This is upper bounded by the following. So maybe I should also say, so for every edge E, and for every coupling of the following two distributions, just the distribution induced by conditioning on the edge E being in or out of the matching. So let's say they call it coupling. So maybe they call this coupling gamma. If I look at it, so for any coupling of the two conditional distributions, if I look at the expectation of a random sample under this coupling, and look at the Hamming distance between two matchings. Okay, so just the number of edges in which these two matchings disagree, that this is an upper bound on the total influence of that edge E. And then I'll use this lemma to then, so then what we'll then do is then construct this coupling iteratively and use that to prove the claim for matchings. Okay? But this is sort of like the main technical lemma that relates coupling and spectral independence. Okay? Yeah, question?
What do you mean by couple?
So I guess I say, so coupling, let's say I have two distributions mu and nu, is joint distribution over, like, say, support of mu and support of nu. Make sense? Yeah, good question.
Sorry, what is pH?
So yeah, so this is like, think of it as, or maybe it's easier to write this way. So just look at the symmetric difference between these two matchings. Just a set of edges in which, like, one is in the other and one is in one and not in the other. Question?
Optimizing over couplings, can you do the right-hand side as some kind of optimal transport?
Yeah, so you can think of it as like optimal. I mean, this is, yeah, so this is like exactly like Wasserstein distance, but with respect to Hamming distance. Yeah. Good question. Mm-hmm. More questions? Okay. Yeah. Yeah, so that's a bit, yeah, you're right. So at least for matchings, okay, so for the conditional independence property, this global Markov property, it just says that if I have two graphs that are like, there are no edges between them, then a uniformly random matching is just given by sampling uniformly random matching here, and then independently sampling another matching here. Okay, so that one is sort of immediate. I guess the only thing is this marginal boundedness, and that can also be verified using some sort of calculations, but I don't want to get into those details. But you can do it.
But what's a matching?
Ah, sorry, okay, yeah, maybe I should not assume that. So I just mean, so a subset of edges, let's call it M, such that, you know, every vertex has at most one edge. More questions? Okay. So I guess in the interest of time, okay, so I guess I'll very quickly sketch. So I guess, oh, sorry, I should also say this is due to Chen and Zhang. So I guess I'll very briefly sketch the proof of this, and then maybe I'll postpone to the next lecture, like the actual construction of this coupling. Okay, but the proof of this lemma is not too difficult. So, okay, so essentially all I have to, what we really have to do is kind of convert this influence quantity into something that looks more like a, so maybe I'll say it this way. So we use something called a coupling lemma, which gives an alternative characterization of total variation distance. Okay? It says the following. So if I look at the total variation distance between mu and nu, and this is equal to the inf over couplings of the expectation under a random sample, say sigma prime, of just the indicator that sigma is not equal to sigma prime. So something called the coupling lemma. It just gives an alternative characterization of total variation distance. Okay, so so if you want to bound this thing, it suffices just say, couple them in such a way that, with very high probability that the two samples I get actually agree perfectly. So we're going to use this. Essentially, how this is going to go is then we're just going to relate this object here to a total variation distance, use the coupling lemma to then relate that to a coupling, and so on. Okay. So we're just going to use this. I'm not going to prove it. Okay, so then proof of the lemma just goes as follows, right? So if I fix, fix any particular edge f, and I look at this difference, and this is really just exactly equal to, it's using, like, say, the L1 definition of total variation distance. This is just the total variation distance between the marginal distribution induced on the edge f, condition on E, being in the matching, minus the same thing, except now I have condition on E to not be in the matching. Okay. So this is more just a calculation using the L1 definition of total variation distance. And now I can use the coupling lemma to relate this object to a coupling, and I sum over all the edges f. Okay? So if I sum over all edges f, so maybe, so this is equal to in for a coupling of these two distributions. Of just the expectation that, the assignment for f agrees in M and M prime. Here I've drawn a sample from M and M prime from my coupling. And I can just sum this over all f, pull the infimum out of the sum, and that's the claim. Okay. So here we just use two different notions, two equivalent definitions of total variation distance. Question? Sorry. So this is, this one here. So this is just, I'm taking a coupling of two conditional distributions, one in which I have condition on E, the edge E being in the matching, and the other one condition on edge E being not in the matching. Yeah. Sorry. Yeah, it's not very legible. Okay. So I guess since it sounds like, or how much should I take?
It's a bit flexible. If you want, you can go a few more minutes, or we can take the 10-minute break now.
Okay, maybe we'd take like 10-minute break now, and then I'll finish the proof like, in the next half of like the construction of this coupling. Okay, so I'll stop here. Okay, hi everyone. Thanks for coming back. So I guess first just ask if there are any questions about what we're trying to do here now. So just to recall from what I talked about earlier, so I guess what I want to prove to you is using a coupling method, prove that spectral impedance holds for the uniform distribution over matchings of a bounded degree graph. Okay? And what we saw earlier is that really you can actually relate these influences that appear in the definition of spectral impedance to, say, coupling. Okay? Okay. So what this says is the following. Okay, so I want to now construct this coupling. So I want to construct this coupling, or in other words, I want to sample. And now, since I'm using this just as a mode of analysis, I don't actually, the sampling algorithm does not have to be efficient at all. So I just want to sample two matchings from, say, a coupling, say, mu. So I'm going to use the notation like E and like E bar. So just E just is conditioning on the event that E is in the matching. E bar is just the event that I'm conditioning on the edge E to not be in the matching. Okay? So I want to sample these two matchings from some coupling, minimizing at least an expectation, so the number of disagreements between these two matchings. Okay? So we're going to do this iteratively. Okay, so let me just draw like a picture here. Okay, so just imagine these two big balls are, it's my graph G. And let's say I have my edge E. Okay, and at the moment, this is the only edge of disagreement. And what I want to do is I want to sample the matching, like complete this to a matching, or sample a matching for the rest of the graph in such a way that I minimize the disagreements in between these two matchings. Okay, so let's do this iteratively. Okay, so for instance, so let's say I have these two endpoints, U and V, and maybe they have some edges coming out of it. Okay. So let's, before constructing the full coupling, let's just try to couple the assignments for the edges that are like incident to U, that are not equal to E. Okay? So let's first try to couple, say, edges F incident to U, say F is not equal to E. Okay? So I want to couple these guys here. Okay? Just for now. Okay? We're not constructing the full matching yet. We'll then do this inductively. Okay? Okay, so here's a claim. In any coupling, okay, and this is where we'll really use the matching constraint. In any coupling, the number so if I, maybe I'll write it this way. So if I draw a sample sigma U, in any coupling of, let's say, let's try this way. So in any coupling of these two distributions, so okay, so I have these two conditional distributions. I'm looking at only the edges that are incident to the vertex U for convenience, right? So in any coupling of these two distributions, if I look at, say, the two samples that I get from it, then a number of discrepancies, or a number of disagreements, is at most one in any coupling. Okay? So is the statement clear? So I'm looking at these two conditional distributions, and I'm just looking at only the edges that are incident to the vertex U. And I claim that in any coupling of these two distributions, the number of disagreements is at most one. Can anyone see why that's the case?
It is included that there's no neighbors.
Right, exactly, right? So this is
Included, that's at most one.
right. So yeah, so good, very good. So this is really just by the matching constraint, right? So in this picture, if E is in the matching, all of these edges are automatically not in the matching, right? So I can just kill all of them. So it's really a question of how many edges here can be in the matching, and there can only be at most one, because they all share the common vertex. Right, so this is just by the matching constraint. Okay, I can only propagate disagreement to one neighboring edge, at most one neighboring edges. Okay? Okay, so now we kind of have like two cases, right? So we have kind of the bad case and the good case. So the good case is that really we couple all of these edges perfectly. Okay? So couple all edges incident to U perfectly. Okay? And let's say that also happens for this side as well. If that were the case, then we would be done. Okay, so what I claim is that I guess maybe it's easier to first. Let's see. Okay, yeah. So okay. So this is the good case. And I guess the bad case is disagreements propagate. Well, they only propagate to at most one other edge. Okay. Okay, so what do I want to have happen then? What I want to have happen is that with very high probability that these disagreements do not propagate too much, that eventually they'll stop disagreeing. Okay? I want so note that the moment the disagreements stop propagating, that I can couple all the remaining edges perfectly. Okay, all of them. Right? So here's an observation. The moment these stop propagating, then we can couple all remaining edges perfectly. Okay. So I'm running this coupling procedure, so I'm going to try to couple these vertices, and then if there's a disagreement, I'm going to keep coupling from there on. Okay. So we can kind of see what will happen is because of this constraint that these edges or these disagreements, they only propagate to at most one other neighbor. What the disagreements look like is the following. So they will look kind of like a path or like a cycle in the graph, and then all of the other edges that you see along the way, they will all be forced to be out of the matching, okay? And they will all agree. So in some sense, it's like surrounding this area of disagreements is agreements. Okay, so agreements kind of surround all the disagreements. Okay. And if that's the case, then afterwards I can just couple everything perfectly outside of it, right? Because I've kind of cut out, all of the edges that are disagreeing in my current matching. Okay? Does that make sense? Believable? Okay. So really, it suffices. Okay, so I guess because of this, so it suffices to bound probability that a disagreement propagates in one step. next claim is just that if my graph is sparse or has bound at maximum degree, that this probability is at most some quantity that just depends on the maximum degree. So the maximum degree is a constant, and this is some constant probability that, some constant upper bound on the probability that the disagreement propagates. Okay? Okay? So in particular, if we could prove this, then basically what you expect to see is that with very high probability, after only a constant number of steps, the disagreements will just die out. Okay? And then that'll yield a constant upper bound on, this expected number of disagreements. Okay? Is that clear? Okay. Okay. So maybe I'll just very quickly prove this, and then we can move on to some other models. Okay, so here's the proof. So as David said, basically, all I have to consider really is that in the case where I have conditioned edge E to not be in the matching, what is the probability that one of these other incident edges is in the matching? Okay? Because that's the only situation in which the disagreement can propagate. Okay? So suffices to prove that basically the probability that some like exists f neighboring u such that f is in the matching is at most this thing. Okay, so this is really the statement that all you need to prove. Okay, and this you can do with some calculation. I won't go into the details. Okay.
So sorry, can I ask, so are you proposing a coupling, or are you saying if I sample uniformly, like if I sample like the, distribution edge is not in the mark, like, it's not clear to me what you described, what coupling you propose. Are you proposing like, sample from one, sample from the other independently, or are you coupling them in some way?
Sorry, so I'm trying to couple them sort of in the optimal way. So I want to construct this coupling iteratively. So I want to couple all of the edges incident to or neighboring E as much as possible to minimize the disagreements. And then from there, if there is a disagreement, then I say couple, say the edges outgoing from that disagreeing edge, and so on, and hope that eventually the disagreements will die out, basically. Okay, that's basically. Okay.
So, but you have to complete this at the marginals of the right.
Right, so it's of course conditioned and everything before, right? But this is, for instance, a generic statement, right? So for instance, I can condition on anything before, I get a uniform distribution over matchings of a smaller graph, basically. Okay, so I guess I'm just saying, maybe you have to believe me, but this is like more of a calculation rather than, like there's not much profound, nothing profound happening here.
Is it clear how to combine this with the V thing? I mean, sorry, I guess you also have the other vertex, right? Is it clear how to combine these things?
Yeah, sorry. So I guess you'll couple from both sides, right? But eventually, either this will grow out to be a path, or they'll like merge eventually.
Edges, so you might, then it seems that if you have two edges, then you're not back in the same case as before. The nice thing was, what you described is that it was, like you start with one edge differing, and then you look at the neighbors of U, and then you only have one edge differing.
Mm-hmm.
And so at most have, or you always need this one edge where things are different.
I see. Okay, yeah. I guess there is that edge case. Okay, yeah. I didn't want to go into too much details on that, but for the most part, I just wanted to sketch a rough idea of the coupling, right? So just if you just sort of couple from there on, but you can also handle that case. Yeah. I don't want to go into details there.
So the clear case is like if you have trees where you can.
Yeah, it looks. Yeah, they look kind of like a tree in some sense. Okay,
Any
Sorry, second. No, I'm not assuming anything like that. I mean, there could be an edge here. That's totally fine, but that lemma will still hold, for instance. Yeah.
This remains a path or a cycle.
Yeah.
Right?
Yeah, exactly. But the point is that the set of disagreeing edges will always be a path or a cycle in the graph. Okay. More questions? Okay. So now So I want to like kind of switch gears away from coupling to like I guess like a more difficult model.
Sorry, so you're saying
Well, okay.
this suffices to prove target? You're just saying it's a calculation?
Yeah, it's a calculation. I'm trying not to.
Okay, you don't want to do that calculation, but it's an exercise for everyone.
Yeah, it's not too difficult.
Okay,
Yeah.
perfect.
Yeah. Okay. More questions?
Can we talk a little bit more about the observation? I don't really understand why, like, the disagreements just kind of stop.
Okay. Yeah. So, good question. So it's not that. So my claim is that if they do stop, so if they stop at some point, then I can couple everybody else perfectly. And that is all it suffices to do is then make sure that they stop with very high probability, and and then that part is controlled by this limit. Okay. So if they stop at any point, then I can couple all the remaining edges perfectly. Okay. Right. So this is why. So. Okay, so notice that, I'm coupling these edges, and I have the path of I have a bunch of disagreements, right? Now, as I'm visiting edges, the disagreements only propagate to most one neighboring edge, and all of the other edges, they'll agree. Right, so that's like this observation earlier, that in any coupling of like those neighboring edges, there's only at most one new disagreement, right? All of the other edges will always agree, right? So the picture you have in mind is that the set of disagreements looks like a path, and then it's kind of surrounded by edges that are all agreeing. Because all these other edges, they must be forced to be out of the matching, right? And then once I've separated out, I've kind of cut out, like, done some surgery and like taken out all the disagreeing edges. All the edges out here, they're no longer influenced by these disagreeing edges, and so I can couple them perfectly. Like the distributions are now identical. Does that make sense? Okay. More questions? I'm sorry. Yeah.
What happens if your max degree is very large?
Yeah, good question. So this kind of thing will not work. At least I don't know how to make it work. Probably shouldn't work. But okay, there are other techniques that will allow you to also prove that, say, at least a related dynamics mixes. This is a work of Jeremy Sinclair from like the 90s. But yeah, good question.
Given this locality, and with the bounded degree case, is it possible to de-randomize them with a small number of random seeds and run deterministic?
Interesting question. I'm not sure. I mean, so I guess there is something. Yeah. Okay. Yeah. I guess the short answer is I'm not sure, but we can talk more about it.
You mean it's not working to maximum degree is not effective? You mean it's not mixing in all the time, or it's not repetitive?
Oh, if maximum degree is not bounded? So we know it's by some other method that it's still polynomial mixing. We don't know it's analog and mixing. We don't know that, but we know it's rapid mixing, like polynomial mixing, via some other method.
Global dynamics is not going to be that mixing.
Global dynamics, I think, okay, I guess it's not written down, but I think it probably is polynomial mixing. So the delta squared comes from, yeah, sorry, yeah, again, I really wanted to hide calculations as much as possible. So if you believe this bound of like this, then the kind of expression you'll get is now what is the expected number of, times that this thing propagates. It propagates with, so it propagates k steps roughly, with this probability, right? And so if we take expectation, it will look something like this. And if you calculate this thing, it's like delta squared, basically. Well, there's a k here. There's a k here. So I'm looking at expected number of them. Yeah.
So it propagates, so it stops at the probability over.
Sorry, what's up? Oh, okay. Okay. More questions? Okay. Yes, maybe. Let's do this. Okay, so I kind of want to switch gears slightly to be for a slightly different, it'll be for a different model and with a different technique, but of a similar flavor. Okay. So there's this thing called correlation decay. So correlation decay, this is like a very fundamental like structural property of the distribution that was, I guess, identified by physicists. And I guess I want to illustrate this method and for the following class of distributions, which is sort of fundamental to like TCS and statistical physics. Okay? So the input is a graph G. Of maximum degree delta. And I want to fix also a positive integer q. Okay. And my distribution is the following. U is uniform over proper q colorings. Okay. So just to be clear what a coloring is, it's just an assignment of colors to all the vertices such that neighboring vertices do not share the same color. Okay. Okay. So this is like various like, fancy statistical physics names, whatever, but at least it's a very fundamental distribution in like TCS and combinatorics. And I guess in some sense, so our goal is of course to sample from this thing. In some sense, I guess one other reason that this distribution is important is because kind of whatever technique you invent to like, solve this, to sample from this distribution, that technique, at least if done in the right way, it should kind of have like many other applications to other models as well, okay? And it's also motivated by sort of a long-standing conjecture. There's a conjecture, this is kind of folklore, but it's been open for many decades, which is the following. So if the number of colors q is at least, say, the maximum degree plus 1, then it exists an efficient sampling algorithm. Okay. And kind of complementary to this is that actually the following, I guess to me, a kind of surprising result, which is that, so it's also known that if q is below this maximum degree, then it is NP hard. Sample. Approximately. I guess, so this is due to Alanis, Stefan Kovic. Okay. So this is an example of something that actually occurs in all of these like statistical physics models, which is that it's like a computational phase transition occurs. Okay. So at least conjecturally. So it's like a computational. So typically there will be some parameter that you're varying, and there's some threshold at which here it becomes NP hard, and here it becomes easy. And really, like a beautiful insight from, like, say, the statistical physicists is that this is intimately related to, like, the structural properties of the distribution. And the particular structural property that I'm going to tell you about is this thing called decay of correlations. I guess I should say maybe also what is known about this and from the perspective of positive results. So it's known that if the number of colors at least, say, twice the maximum degree, so this is due to Jerem back in the 90s. Okay, maybe I'll just say what the current state of the art is, maybe. So results if number of colors is at least some specific threshold, 11 over 6 minus some epsilon times the maximum degree, then there's efficient sampling. Say Glauber. And n log n steps. Okay, so this is due to, I guess, I mean, okay, I'm just going to put all the names here. So what is the structural property that I want to tell you about? So what turns out to be sort of what happens in some of these statistical physics models is the following. So in the easy regime, what we expect to happen is the following. So if I look at my graph, I fix, say, some arbitrary chosen vertex R. Okay. And I look at, and suppose, suppose I tell you like the value of the colorings, or the colors assigned to all the vertices along the boundary of this big ball. What turns out to be really helpful for sampling algorithms is the following property, that actually knowing this information, knowing the values of the colors for all these vertices along the boundary, gives you very little information about the vertex U. In particular, the correlations are very small in terms of the distance between R from the boundary. Okay? This is formalized, so this is formalized as follows. So I'm going to define something called strong spatial mixing. So maybe let's call this. It says the following. So for every vertex R, and every pair of, say, configurations on, let's see. For every subset of vertices, say not including V, and look at every pair of configurations mapping the subset, say, to colors, and I want to compare the induced conditional distribution on the color assignment for R. Okay? So what we say is following. So I compare the marginal distribution induced on the vertex R condition on, say, these two assignments, that they are small in total variation distance relative to the distance between R and, like, say, the boundary. So I guess the more correct thing is, so this is the set of vertices such that these two color assignments disagree. Okay. So this is one way to formalize what it means for correlation decay in the graph distance. It means that, you know, no matter what pair of colorings I choose on the, say, a boundary of a big ball, for instance, the total variation distance between the induced marginal distributions is small relative to how far that vertex is from where the boundary of the ball is. Okay? So this is like some notion of correlation decay. Okay. So questions about this, what this means. Okay? So this is a fundamental structural property of the distribution, and it turns out to be, you know, really important, for instance, for getting fast mixing or getting sampling algorithms in general. Okay?
So is that as a set or a number? Or
Which one? This one?
is, this
Oh, sorry. Sorry.
Where's big R factored into this?
So big R is like this distance here. This is like R. Sorry. Yeah. Yes, maybe that's it. More questions? Okay. What is what? Okay. Okay. Yeah. Sorry. It's this thing. So think of, yeah. So here's a drawing. Just think of lambda as being the boundary of this big ball, and then R is like the distance from R to the boundary. Sorry. Okay. So now I want to tell you, like, okay. So this is a structural property of the distribution, and I want to tell you what consequences it has for what exactly it means for fast mixing. Okay. So first, the way I define it, spectral independence is really only for distributions on the Boolean cube. The generalization of spectral independence is the following. So for colorings, so now we're going to define, really just think of the influence matrix as now being on NQ by NQ. Think of now the columns and rows are indexed by vertex color pairs. Okay. And now you think of the influence of, let's say, a vertex color pair, say U and C, V and C prime. This is probability that I sample a coloring that assigns V to C prime, condition on assigning U to C, minus the probability okay. There's a slight difference here where I have not conditioned on anything in the second term, but okay. But this is sort of the right generalization for colorings. Okay. So at an intuitive level, if I have something by like exponential decay of correlations, then I should say something like, so intuitively at least, so correlation decay will imply that the rows, so the entries, or I guess, yeah, so I guess you could say maybe implies that this influence is exponentially small in the distance between U of V. Okay? Intuitively, right? I mean, really, for instance, really you're just comparing the marginal distribution induced at V based on whether or not you condition like what you have assigned for vertex U. Okay? So in particular, this says something very structural about the influence matrix whose eigenvalues we are trying to bound. Right? It says that all the rows and columns, they're kind of decaying exponentially fast. Okay? And truly, that says something about its eigenvalues, although it's in general it's not obvious, but at least intuitively, it says something about its eigenvalues. Okay, I'll say it. Okay. So intuitively. So intuitively implies okay, but okay, there is work to do here. Okay. So what I plan to do for the rest of the talk is I'm going to state just going to state some newer results on colorings, and I just want to give you like a rough outline or a sense of how would you establish something like exponential decay of correlations. So this is recent work that's joint with Nityamani. So I guess Zhongchen Chen. And Anker. So following theorems. So for trees specifically, strong spatial mixing holds. As long as number of colors Q is at least maximum degree plus 3. Okay, so we're just slightly away from like the conjectured threshold. Okay. And the second theorem is that this has consequences for algorithms. So in particular, so let's say, suppose I give you a little bit of extra colors, 1 plus epsilon times the number of times the maximum degree. Then Glauber dynamics mixes order of n log n steps assuming, say, the girth of G is at least, say, okay, so some f of delta, I guess the exact dependence is something like log squared of the maximum degree. Okay. So in a recent work, so what we do is we prove that for the special case of trees, we have strong spatial mixing, this notion of decay of correlations, and then we managed to show that this implies actually something about fast mixing for Glauber dynamics, at least if the girth is sufficiently large. Okay. Questions about the statement? So epsilon is just some small constant I give to you. It's like a parameter. So I give you epsilon delta many extra colors. And right, so I guess that there will be some dependence on epsilon. Yeah, question?
Is it possible to extend the strong spatial mixing result to the general graph with large curves?
Good question. Not sure. Probably doable, but not sure. It's like a little bit unclear.
Right now, Kuikui, should it be obvious to me how you get to from like the second theorem from the first theorem, or?
No, not at all. Not at all. I mean, I was going to try to give you a sketch of like why that works. And right. So in the remaining time, in the remaining 15 minutes, I want to just say a few things of like how you might prove something like this. Okay? Okay. So really, like the main theme here. So maybe it's better to start by maybe talking about a slightly simpler model where we know much more. So, but mainly the theme here is to basically reduce these kinds of questions. Reduce to trees. That's the main theme. And I guess I'll just say that right. So maybe I'll okay. So I'll say something. Okay. So I'll say what was known previously for a much simpler model. Okay. So this is known. So for a simpler model. Which sort of will give some indication of like why such a strategy should be possible at all. Okay. So this is a theorem to the bytes. Okay, and it says the following. Okay. So for a graph G, so let's see, fixed G. So I'm looking at a slightly different model, a simpler model, where I'm going to have a weighted distribution over independent sets of a graph. So just remember, an independent set is a subset of vertices such that no pair are connected by an edge. Then, for a vertex R, there exists a tree T, which depends on the graph G and the choice of vertex R, such that the following holds. Okay. So first, the maximum degree of T has the same maximum degree as G. And perhaps more amazingly, if I look at, say, the probability, so maybe let's also say this is rooted at the vertex R, such that the probability is, like, say, if I sample a random independent set, that the root R is in the independent set, is the same if I look at it under the tree T. I mean, this theorem is not supposed to be like obvious, but I guess I'm just trying to say like there's been precedent for this kind of result. This tree is sometimes called like the tree of self-avoiding walks, if you know what that is. But the point is that you can reduce these kinds of questions about, say, correlation decay or even like computation of, say, the marginals of like a vertex to a question just purely on trees. Okay? So you should think of this at a very intuitive level. This tree is formed by like a certain computational process for actually computing the marginals. But I'm not going to get into the details there. Okay? But this is like kind of like one of these like really striking results because somehow you've reduced the complexity so much. I've somehow gone from an arbitrary graph to like just a tree.
So it could be like in the tree of self-avoiding walks,
Hmm?
I mean, to map an independent set from the graph to the tree, it's not like the vertices are independent in the tree like they would be in a tree.
I mean, so there's some way to like map a vertex in the graph G to the vertex in the tree,
Yes.
and right. I guess so.
But I mean, okay, but it's not like now I can, if I analyze trees, then it's obvious that I can pass the graph because this tree of self, like the way that the independent set maps from the graph to the tree of self-avoiding walks means that if I include some vertex, then I have to include its copy like later down in the tree, right? So
Right. So there's some way to say now if I have fixed some choice, some pinning of all the vertices of some vertices in the graph G, that will map to some pinning of the vertices in the tree.
yeah.
Now I can start like say comparing these two things. So maybe I'll just say
Like I'm just saying, you haven't reduced the complexity so much that I can now analyze the independent sets on a tree, an infinite tree, and get the same answer.
in a way yes, because once I've because
Like you're just gonna now there's an additional step where you have to say if I go to high enough radius then I'm fine, or
right. So I mean, in a sense, this is saying that you can reduce to just independent sets in a tree, because if I say condition on some vertices to be in or out, that just corresponds to like deleting those vertices. So really, I actually have just a tree, and I'm computing, say, the marginal probability of the root of that tree. But there is like a
The Weitz result is a miracle.
yeah.
But it's just the tree itself you construct is exponentially large.
Yeah. So I guess I should say yeah, right. So the tree turns out to be exponentially large, but.
The problem on the graph, the problem on the tree, but tree is exponentially large. But if there is correlation decay, then you don't have to compute it on the entire tree, but small part of it.
Okay, sorry, yeah, I'm sorry if I misunderstood the question. Okay, and I guess I should also say that there is some kind of an analogous tree for the case of colorings, except for somewhat technical reasons, it's much harder to work with. In particular, it branches at a much larger rate. Okay, but I don't want to get into details there. Okay, but I guess what I wanted to point out is that like this kind of results suggests that like this is possible, that you can reduce this question of trees. Yeah, question.
Do you need any additional assumption on each lambda? Does it hold every lambda?
Yeah, so this will hold for every lambda. So this holds for every lambda. But now it becomes a question of like, for what values of lambda does, for instance, do I have correlation decay in the tree? Yeah, good question. Okay. More questions? Okay. Okay. Yeah, so I guess I don't have so much time, so let me. Okay, so let me just very briefly outline how you can reduce it, do some kind of reduction in the general case when you have, if you make an additional assumption that the girth is large. So more general reduction. Yeah, general reduction in the large girth setting. So first off, like, the reason that you want to assume large girth is just because now if I look at, balls around any vertex, those are trees, basically. Okay, that's the reason that we want to assume large girth. Okay. So let me state sort of like a technical lemma that, I mean, hopefully just gives some inkling of idea of like why this reduction is possible. Okay. So here's the lemma. Trees. So I'm assuming strong spatial mixing holds only on trees. Okay. Then if I look at, so here's the picture. So now I have a general graph, but I assume it's large girth. So let's say this is vertex R. This is G over 2 radius, so G is the girth of the graph. If I only look at this radius, then basically this ball looks like a tree. And what I want to claim is the following. So if I assume strong spatial mixing holds on trees, then for all, say, colors B and C, if I look at these distributions where I have condition on the vertex R to be, say, assigned color B versus condition on make a different choice of color for the vertex R. And if I look at just the marginal distribution induced on the boundary of this ball, okay, so let's say, let's say this is. So here, I just mean the boundary. This ball, this is, at least in total variation distance, at most, up to some constants, exponentially small in the radius of the ball. Okay? And this is really using the fact that this ball really is a tree. So at an intuitive level, if you believe this statement, right, what this says is that now if I imagine try to run this coupling procedure or design some coupling procedure similar to what I did for matchings, that if I sample a coloring on the boundary of this ball, that they should agree perfectly with high probability. Okay? And as we said earlier, and similar to the situation for matchings, if I can contain all of the disagreements within, say, the ball of radius G over 2, if all the disagreements are here, and I've coupled the boundary perfectly, then I couple everything outside of the ball perfectly. And so the total number of disagreements is just at most the number of vertices inside the ball. And since G is, say, a constant radius, then that's like a constant upper bound on the number of disagreements. Right? Now, of course, like this is by itself is not strong enough. I mean, this is, we have zero control in the bad case where we failed to couple, okay? So I don't want to get into technical details there, but this is sort of just hopefully like a little suggestion of like why, or a little hint of why such a reduction is possible. Okay, so I don't want to get into too much more details there. I hope that's like somewhat explanatory. Okay, so I guess maybe in the last 3 minutes I'll just say, briefly outline like, okay, so suppose you believe this. Suppose you believe that strong spatial mixing on trees implies something, say, for spectral independence, or implies something for general graphs, okay? Then how would you establish something like strong spatial mixing on trees, okay? So, say spatial mixing. And this really just comes from the following fact, which is that there's a recursive way to compute, say, marginals of vertices on the tree. So just imagine, okay, so I guess here's a picture. So I imagine I have a tree T. It's rooted at some vertex R. And I have, like, say, some neighboring vertices, say U1 through UD. And they induce some subtrees. Okay. Then there's a way to recursively compute the marginal probability that if R is assigned some color based off of the marginal probabilities for its children. Okay. So, okay, I'll just say, okay, I won't write out the formula, but there's some, okay, maybe I'll just write it out, it's fine. If I look at the probability that, say, R is assigned a color C, this is given by the following formula. It's not so important what this formula says. All that matters is that there's some way that given the marginal probabilities or the marginal distributions for the children of my root vertex R, there's a recursive way to compute the marginal distribution for R. Okay? And then you can imagine what correlation decay, how you can approach correlation decay is the following. You want to say that if I fix two different choices of colorings for the, say, the leaves of this tree, that they will have very negligible effect on the marginal distribution for R, which corresponds to a kind of like stability property for this computation. Okay, corresponds to the fact that, for instance, that this computation, this recursion is like a contraction, basically. Okay, but that's like a very, yeah, it's a fast way to say it, but okay, maybe I've said enough technical things. Are there any questions about anything? Well, that's just a very brief sketch. Oh, no. So this is something very specific to trees, right? So really for any of these models, like colorings, independent sets on trees, there's always an exact dynamic programming or like recursive way to exactly compute all of these marginal probabilities, and from that I can do exact sampling and everything. But what turns out to be crucial for this structural property of correlation decay is how, like, roughly how stable this recursive algorithm is for computing these margins. Okay? Very roughly speaking. Yeah, I guess, yeah, good question. So I guess,
I mean, like, you pay for the size of the boundary, but you don't pay.
yeah, so, right, good question. So technically, I'm lying to you a little bit. Typically, we open up the proof of strong spatial mixing for trees and use that to do something about this. There's a kind of trick with Bayes' rule here where you kind of flip the conditioning, but maybe we can take that more offline. That's a more technical question. But yeah, it's not obvious at all. I'm not like